Yeah, thank you. Yeah, first of all, I want to thank the organizers. And yeah, so the title of my talk is on the generic inverse problem for the classic group. Well, it's a generic inverse problem for differential Galois theory. And our main basic object of studies are the classical groups. So let me quickly introduce some notation. Don't be afraid. It's standard notation, so you don't need to know to remember all this notation. So by G, we mean one of the classical groups. By fracture G, over here we mean its Lie algebra. By phi, the root system of the group, which corresponds here to the to AL, CL, BL, DL, G2. By delta, we mean a basis of the root system. By alpha 1 up to alpha L, we mean the simple roots. Phi plus denotes the set of positive root, phi minus the set of negative root. And by calligraph W, we mean the Weyl group. Well, we fix a maximal torus, which we denote by T. Then we have a root space decomposition of the Lie algebra. Here H is the Lie algebra of the torus, and we have here the one-dimensional root space for each root beta. We also get fix a basis. Here the capital H are basis of the Cartan subalgebra, and capital X with index B is the basis element for the one-dimensional root space corresponding to the root beta. Well, we also fix the Borel subgroup. Here the Borel subgroup with Lie algebra. So the Cartan subalgebra plus the root space for the positive root, and we fix its opposite Borel subgroup as the corresponding Lie algebra. Then we have the maximal unipotent subgroups and the opposite with the nipotent, maximal nipotent subalgebras, U and U minus. Then, well, this is standard, and you don't, if you know the theory of Lie groups, then this notation, you don't really need to remember this notation. And well, here by capital U beta for root beta, I mean the root group, and well, the root group is isomorphic to the additive group. And for, well, when we number the negative roots for an element xi of the field, I mean by U beta, little U beta, I xi, the image in the root group, and by bold symbol ux, I mean the product of these images. And this product I will call a unipotent element for x. Similar here for the torus. Well, the torus has one-dimensional subgroups isomorphic to the multiplicative group, and then for a multiplicative element, I denote by Ti Z1 the image of this element in this subgroup. All right. So really some time ago, I determined for the classical groups very nice and explicit linear differential equations, parameterized linear differential equations. So what do I mean by that? So we start with L differential indeterminates T1 up to TL and look at the field CT generated by these indeterminates. And by a linear scalar parameter differential equation, I mean a scalar differential equation with coefficients at differential polynomials in the indeterminates T. All right, so here are the equations. So this is the first equation. This is the equation with scalar groups, a special linear group. And you see it's a pretty easy and nice equation. So second equation is the equation for the symplectic group. Still easy, fits in one line. Nice. The third one for the orthogonal even dimensional. Still very nice shape. The fourth one is for the orthogonal odd dimension, the other way around, even dimensional. Here it's getting a little bit bigger, and we have here to make the first substitutions, but it's still something you can write down. And number 5 is an equation for G2. Well, since we used here differential indeterminates or parameters, we can specialize these equations. So each equation defines a family of equations. So a question which bothered me for a long time is the question, what are the generic properties of these equations? So if you have a Picard-Wessel extension, does there exist of Picard-Wessel extension with the corresponding group? Does there exist the specialization of our equations such that this extension is defined by specialization of our equation? All right, let me quickly say something about the construction of these equations. Well, actually, the idea was to take a specific element in the Lie algebra of the group. So this element is denoted by AGT. What is AGT? Well, it's the sum of this element A0 plus, where A0 plus is the sum of this basis element corresponding to the simple roots, positive simple roots. Then we pick L negative roots, specific negative roots, so the choice is important, and set the parameter in front of these basis elements. So that's the choice of the defining matrices. Well, to answer this question, let's have a look what have people done classically. Yeah. So, I will just explain here this in the classical Galois theory. So everybody attended a lecture or already gave a lecture in algebra. So what you do when you want to compute a general equation with for the symmetric group. So you start with a general extension field. That's meaning you take n indeterminates and look at the rational function field generated by these indeterminates. You define a group action on this field, and you look at the fixed field of this group. Then you know by theory that this is a Galois extension, and you have here the corresponding equation for this extension, where here these are the elementary symmetric polynomials. And well, what you can show then, or what people know, or what is a fact, is that the fixed field here is then a rational function field and the elementary symmetric polynomials, and they are algebraically independent. So that's pretty standard. Something similar you can do here in differential Galois theory. All right, so let's come back. We started with a differential transcendental field and constructed an extension and an equation and an extension, and well, this equation has differential Galois group G. So the question is now, can we start also with the other way around? Can we start with a general extension field, define a group action on it, and look at the fixed field? So this is the first question. Can we construct a general extension field E on which G acts, such that the field of invariant is a Pauli differential transcendental extension of C, and the fixed field, or well, E is over the fixed field a Pickett-Wesset extension for our defining equation. So, and then what are the generic properties of this extension and this matrix AGH? All right, before we start with the construction, we need to connect the group structure, or we need to establish a connection between the group structure and Pickett-Wesset extension. Well, in the structure theory of reductive groups, the Brühart decomposition is an important result. So what the Brühart decomposition says, or what it does give, is a normal form decomposition of elements of the group. So for a fixed Borel subgroup. So what does it mean? So for each element of the Y group, fix a coset representative NV in the normalizer of the Y group. Further, we have for each Y group element the subgroup U prime W, which is a subgroup of the maximal unipotent group determined by this Y group element. So and now every element of X can be written as a product of an element U prime coming from the subgroup times a representative of the Y group element times a torus element times another unipotent element. Okay, so we want to focus on specific kinds of Pickett-Wesset extension. So what do I mean by a full G primitive Pickett-Wesset extension? I mean a Pickett-Wesset extension whose differential Galois group is a full group G, which is generated over F by a matrix Y, and the logarithmic derivative of this matrix Y should lie in the Lie algebra with entries in the field F. So what can we say now about this fundamental matrix Y? Well, we want to apply the normal form decomposition on this matrix. And as I said, so the normal form decomposition depends on a Y group element. So what is the Y group element for a fundamental matrix Y which lies in the group, and which has the full group G as differential Galois group? Well, there's a specific or a special Y group element in the Y group, which is called the longest Y group. This one maps the positive roots to the negative and the negative one to the positive. And what is important here now to know is for this element, this unipotent subgroup U prime becomes the full group, the full unipotent subgroup. So for full G primitive Pickett-Wesset extensions, there are algebraically independent elements x1 up to xm, z1 up to zl, and y1 up to at m, such that the matrix Y decomposes like that. Okay, so let's establish a deeper or further connection. Well, as I said, Borel subgroups are important subgroups and they are maximal solvable subgroups. So in Pickett-Wessel theory, a Pickett-Wessel extension with a solvable subgroup is a special kind of extension. It's a Liouvillean extension. So what we just can do, we can look here at we can use the Galois correspondence and get here a Liouvillean extension. Yeah? So yeah, that's trivial, or that's obvious. But can we say something about the generator of this extension? Yes, we can say something about. So take simply an element B of the Borel subgroup, multiply Y from the right with it, take the normal form decomposition of Y, and then this part here lies again in the Borel subgroup. So you have here new elements Z tilde, Y tilde, which are elements of the field generated by Z and Y over the constants. So we conclude that this is in the fixed field, right? And this generates this Liouvillean extension. All right, so this is the statement, what I really just said. You can be a little bit more precise. So the ZE, they generate an exponential, they are exponentials, and the elements YI, they are integrals. All right, so that's a nice connection. And having this now in mind, how are we going to construct our general extension field for the classical groups? Well, it should somehow reflect the structure we have seen right now. Yeah. So let's take L differential indeterminates eta and look at this field generated by these indeterminates, and then define a Liouvillean extension of it by this matrix. One can now show that this matrix, is a Liouvillean extension of this with Galois group, the complete Borel subgroup, and fundamental matrix YL, which decomposes like that again, with elements Z and Y, and these are again exponential and these are integrals. So the whole construction is done in such a way that the matrix Y can be written as this product, and the logarithmic derivative of this matrix Y is the defining matrix of our equation. Well, now we can finish the reverse engineering process. Well, let's have a look at this differential field extension. Well, this field generated by the coefficients here of this matrix, and these coefficients are differential polynomials in the etas. Well, first of all, we have to see that this extension is a purely differential transcendental extension of degree L, and this you can deduce from the shape of these differential polynomials. Then you have to see that this is a Pickett-Wessel extension for that field for this matrix, and now you simply can apply theorem 1. So what you get, so this is the whole situation. Here's our field. These are the coefficients of our equation. Then this differential subfield of E is a purely differential transcendental extension of C. Its differential transcendence degree is L. The differential field extension, E for this differential subfield, is a Pickett-Wessel extension with this for this matrix differential equation with differential Galois group GC. So what have we done? So, well, we started with this field, attached a Liouvillean extension to it, looked at the fixed field, and this fixed field is generated by these differential invariant polynomials. Differential invariant polynomials, and they're differentially transcendental. All right, so this is the situation as I explained before for the SLN case, or for the symmetric group, or for the general linear group. So we did this reverse engineering process. All right, so yeah, are these, well, what we have seen now, so if you have a full G-primitive Pickett-Wessel extension of my type, so the only degree of freedom are in these indeterminates. Yeah? So the Liouvillean part then is determined by this. All right. Okay, so yeah, this is a degree of freedom. And so now we want to know which extension do our matrices define. Well, if we have an equation of a full G-primitive extension of our type, it would be really a coincidence if there's a defining, or we know that there is a defining matrix which is of our shape, and then we can simply specialize. Well, what we have to do now is we have to consider gauge equivalent matrices. So what this box here is, this box is the Lie algebra of the group. This red line is the set of all specializations of our equations, and now we want to know, we want to give a condition for this matrix A such that the orbit under gauge transformation intersects this line. So is the matrix A gauge equivalent to a specialization of our equation? All right, so let's have a look at the gauge transformation. Roughly speaking, the gauge transformation can be decomposed in an algebraic part and in a differential algebraic part. Yeah, so the idea here is now to use the root structure of G to describe the gauge transformation. Well, if we transform a matrix by a root group element, then its logarithmic derivative is by a theorem of Colchin or proposition of Colchin. It lies in the Lie algebra of the it lies in the root space of the corresponding root. Yeah. So the logarithmic derivative can be easily described when we transform the root spaces. The algebraic part is well known in literature, so there's a lot of theory available. So let's have a look what kind of theory there is. Well, this here is now purely algebraic. Yeah, so this is the joint action. These are results by Constant. And what does Constant do? Well, Constant looks at orbits of elements, looks at elements which have orbits of maximal dimension, and he calls these elements quasi-regular elements, and the collection of all these elements is denoted by fracture R. Well, he proves the following theorem. This plane here, which is the sum of the following matrices, well, here we have A0 plus, which we also used for the definition of our equation, plus some subspace here, I will not say what it is, that this plane lies here, or all matrices of this shape lie in the set of regular elements. So furthermore, the map sending an element of the set to the set of orbits of all regular elements is a bijection. So now two distinct elements of this fracture V, that is now two distinct elements of a conjugate, and every element in R is conjugate to one and only one element to this subset here. So the amazing thing now is we can substitute this thing here by the root spaces we used for the parameterization of our equations. And the theorem is still true. So in the purely algebraic case, what we have is that if we have a regular element and look at the orbit, just under the joint action, it intersects the red line. Okay. Well, unfortunately, there we have to take into account the logarithmic derivative. And the logarithmic derivative normally destroys something which we already transformed algebraically. But for one specific kind of set, we can control that. And this specific kind of set is this green box over here. And let me just say what kind of matrices these are. These are elements of this shape. We have here A0 plus for an element S, where A0 plus is the linear combination of basis vectors corresponding to the simple roots, plus elements here of the Lie algebra of the opposite Borel subgroup. All right, so as I said, here we can control this, and we have the following lemma. Every matrix here in this green box can be gauge transformed to a specialization of our matrices. All right. What does if we are not here in this box? We need a criterion for that. Well, as we have seen before, the extensions are determined by L elements of the extension. Then there comes, this determines then a Liouvillean part. And the idea now is to decide gauge equivalence by this Liouvillean part or unipotent part. So what we do now again is we consider here this extension, which is defined by the unipotent subgroup U, and we look at the defining matrix of this extension. This is not, of course, a defining, well, A is a defining matrix, and this is a fundamental matrix for this. But since we know that this part here is generated by this elements, and this part up here is generated by these elements, we can produce a new equation for that. It's simply just multiply with the inverse of this matrix. We get this fundamental matrix, and the logarithmic derivative of this matrix is then a new defining matrix for this extension here. And the idea now is to say, or to decide whether such a matrix here is gauge equivalent to a matrix of this shape, which is simply the linear combination of the negative of the simple roots with non-vanishing elements Si of this fixed field, and such an element will be called principal nilpotent matrix in normal form. So when we transform with these matrices, then later on we want to reattach this part to our extension. So we have to do this in a way that it is compatible with the rest of the extension. And well, this lemma shows that we can do this, and elements which come from this lemma I call A-equivalent transformations. So we have now here the following proposition. A matrix A is gauge equivalent to a specialization of our matrix AGT if and only if the unipotent part is gauge equivalent to a principal nilpotent matrix in normal form. So this blue line are all principal nilpotent matrix in normal form, and this triangular is the set as the Lie algebra corresponding to the Lie algebra of the unipotent group. So that's the criterion. So if we can do this, we call such an extension a G-primitive extension with normalizable unipotent part. Yeah. We can now say the main theorem. All the stuff above here we have already seen. Well, now let L be a full G-primitive extension with normalizable unipotent part. Then we have we can say the following. So then there is a specialization such that our specialized equation is defines this full G-primitive extension, or this full G-primitive extension as a Pickett-Wessel extension for a specialization of our equation. And this is just a translation that a defining matrix for this extension is gauge equivalent to a specialization. Well, and of course, if you simply just specialize, then we get subgroups. Well, let's have a look at an example. So how does this look like? Well, here for G2, it looks, I think, pretty simple. Here, this is our general extension field for the specific type of extensions we have. Well, G2 has Lie rank 2, so we have two differential indeterminates, and then we attach this Liouvillean extension to it, which is generated by elements of this shape. And then we can look at the invariants under the group action, and the invariants. The first invariant looks still nice, and then the other one is getting a little bit bigger. Actually, what is here true is even more. So this condition here, this normalizable unipotent part, can be dropped. So ever when you have a full G-primitive extension, then there's a specialization such that the specialized equation defines this extension. All right, the same holds also for the special linear group. By the other groups, I don't know. All right, thank you. I didn't yet think about that. Yeah, so this is still work in progress. So so yeah, but yeah, that's something to think about. Yeah. So well, I think the amazing part is that for this kind of specialization, well, they are determined by L elements in the Pickett-Wessel extension, and this is exactly the degree of freedom you have in your generic field, a general field. Yeah.